Assalamualaikum and very good day. This is the lecture about the process and process selection focusing on joining and finishing process. Here's the outline for this lecture, but I'm going to skip it anyway. So joining has three classes, which are adhesive, welding, and fastener. So the attributes or requirement differ from shaping, which include the type of material to be joined together, such as metallic material, polymers, and many more. Another one is the geometry of the joint and some properties such as electrical conductivity, thermal conductivity, and many more. In this figure, among many of the manufacturing process, we can consider assembly is one of the last process in manufacturing. It's either finishing or assembly would be the last. We can see that each of the joining classes has pros and cons. The adhesive can be used to join both similar and dissimilar materials. Nevertheless, the bonding durability is quite low. For example, joining two wood panels with acrylic-based adhesive is better than joining metal sheets using similar adhesive. This is due to the metal surface is generally smooth and stresses are concentrated at the bonding interface. The fastener actually can be used to join various material together, such as screw, bolts, and nuts and rivets. However, this joining method is not permanent and some can be undone by just using vibration. The welding in this case is the largest class of joining. Commonly welding can be used to join metals and plastic, but it requires to join within the similar family of materials. This is some examples of joining description. Over here you have adhesive, okay, and then over here you have a fastener. Here you have the welding, which is the shear metal arc welding, and here will be the polymer welding. In detail, adhesive can bind different materials together, which is cost effective, increase design flexibility, and decrease stability at high temperature, and hard to bind different surface area object. Types of adhesive, which is non-reactive and reactive. So non-reactive adhesive, which is involving drying mechanism, which is glue, rubber, cement, and many more. And then you have the pressure sensitive, which is, for example, double-sided tape and so on. And then you have the contact type of bond, which is, for example, natural rubber and neoprene. And then you have the hot adhesive, for example, the glue gun that you use. And then for the reactive adhesive, you have the multi-part or one-part resin. So you can use, for example, this one is the polyester polyurethane resin, and another one is one part, which is the, for example, acrylic resin and so on. Here is some example for the fastener. So fastener literally mechanically join or affix two or more objects together. So it should be using mechanical force to join materials together. So large volume of fastener is costly due to difficult to automate. So if you have a lot of fastener, probably it costs a lot because you have to invest more on the screws, on the bolt and nuts, and then and so on. So there are types of fastener, which is including bolt, tip, clamp, pin, screw, staple, and so on. Now, although welding is well-known joining process, it is actually much more complicated process since it involves heat. The requirements of welding depends on the material which involves it, in material's properties respectively. Only similar family of materials can be welded together, such as metal with metal or plastic with plastic. Ceramics definitely not, because it is requiring a lot of energy in order to melt it. In general, these are the method for welding metal and plastic. Generally speaking, dissimilar metal welding or dissimilar plastic welding is possible and quite common, such as stainless steel with carbon steel welding, which is requires specialized electrode and specific condition to avoid defects such as stress cracking, at the heat affected zone. Over here is the list of metal welding. Over here is the polymer welding. Okay, so you already know about the sheet metal arc welding, tungsten inert gas, metal inert gas, and resistant welding, oxide acetylene welding, and stir friction welding, which is quite relatively new towards metal welding. Over here, you have the plastic or the polymer welding, which is hot gas welding, extrusion, contact welding, hot plate, high frequency welding, injection welding, and then the ultrasonic welding, friction welding, and also laser welding. Here is the metal welding. Okay, shear metal arc welding, which is quite common to you. So you have a metal inert gas, and also you have the tungsten inert gas. The difference is between these two, the metal inert gas is consuming metal wire electrode. Over here, the tungsten inert gas does not consume tungsten, only consume the filler wire over here. Here you have the spot welding, so using electrical current, uh, and then you have to apply pressure for the copper electrodes towards two metal sheets, and then in between this metal sheet you have actually air or void over here, so current do not easily pass over here, so you producing a lot of resistance in between these two metal sheets. So over here, in between these two metal sheets, so spark happening over here, so then easily melt the two metal sheet in between. And then stir friction welding is relatively new. So over here you have a rotating disc electrode, which is rotating at very high speed, and then it will fuse together on the two plate sheet due to the friction that cause heat. And then for the gas welding, using oxide acetylene as the gas supply, will produce flame or plus similarly like high intensity flame, which fuse together the work fuse together. Here is the example of the plastic welding. The first one over here is using the laser to fuse two polymers. One is the transparent, another one is the absorbing polymers. So you have the weld seam caused by the laser welding. And then here is the stir friction welding. Is similar as the metal stir friction welding. And then here is the hot gas welding. And lastly but not least is the ultrasonic welding. The finishing process is a process to be applied to the surface of the component, which purpose is either to improve the engineering properties such as corrosion resistance, hardness, and many more, or to enhance their appearance. Okay, here is the list of the common finishing processes, which is including anodizing, honing, painting, plating, and polishing. Surface finishing capability is depending on the surface roughness requirement. The smaller RA, which is the roughness in micrometer or microinch, means that it is smoother. Usually the metal cutting method producing rougher surface compared to the abrasive method. Okay, so this one is the cutting method. Here is the abrasive method. Here is some example of surface finishing process. In mechanical polishing, it is actually a material removal method that use abrasives such as machine grinding. In plating, over here is electroplating. You can have either electroplating or electroless plating, which employ superior metallic coating on the workpiece, such as thin plating on copper to increase corrosion resistance against fresh water. Carburizing over here, sorry, which is carburizing? Here is the carburizing. Is a method of heat treatment to fuse carbon on the surface to increase the hardness and chemical resistance. In anodizing, this is actually a method to oxidize the surface of a metal to increase corrosion resistance, such as oxidizing of the aluminium surface to become alumina. This is the brief explanation of the surface finishing method. explained previously. Grinding, lapping, and polishing increase the precision and smoothness. Electroplating deposit a thin metal layer or thin alloy layer on the surface of a component to give corrosion and abrasion resistance, such as nickel plating. Plating and painting are both easy to do, difficult on the surface complex surface. Anodizing and phosphating and chromating are creating a thin layer of oxide, phosphate, or chromate on the surface, preventing continuous corrosion. And here will be the heat treatment, which, for example, age hardening alloy of aluminium, titanium, and nickel. And then you have a quenching and tempering, which is already you have learned in the engineering materials. Okay, this is the fundamental of anodizing diagram. Anodizing means oxidation. So you put the material or the product over here in a solution containing cation and anion. So the purpose of this solution is to oxidize the surface of the product. So when the product become anode, so electron, okay, will lose from the product itself. For example, um, magnesium or aluminium, and then it will merge with the oxygen inside the solution and then producing an oxide. So this oxide, aluminum oxide, and so on, is quite stable compared to the iron oxide. This is the case for surface finishing for enhancing appearance as well as giving application for the product. The most common is the paint spray. So a pigment in an organic or water-based solvent is sprayed onto the surface to be decorated. Sometimes the paint is very useful for the protection, for example, in terms of corrosion protection or weather protection and so on. So there are many types of paint. Sometimes the paint is made from the purely from polymer. Sometimes it will added by with glass flake epoxy. So it become much more harder. So that one is for the marine structure in near seashore. And then the other method would be the polymer powder, which is emphasizing on spraying of polymer powder, and then with the heating, and then this one basically similar like a thermal coating like that. And then another one is the silk screen printing is purely for improving the surface appearance as well as the similar as the pad printing. Silk screen printing is one of the most simple and cheap process involving the use of masking as a screen pattern. So over here you have the screen pattern made from the film positive used to expose the hardened and light sensitive emulsion. Sometimes we can use laser printing or laser beam to burn out or to make a pattern on the surface of a screen, for example. And then this screen frame stretch tightly with the fabric. Then using ink, you pour the ink onto the screen, and then using the rubber squeegees so that you can even up the paint onto the uh, where the area, the one that you want to do the pattern. This part is a little bit detail about the painting. So in case of this one is for the enhancing appearance. So painting using either organic solvent or water-based solvent. So organic solvent is quite durable with high finish coating but poses some environmental issue because it is made from sometimes with made from epoxy and so on. So water-based is less environmental effect and slow drying, hence less perfect. And then you have the polymer powder spraying, which is using the thermoplastic film spraying on the surface, giving a protective layer. In order for you to apply the process, you have to know the compatibility between the materials properties and the manufacturing process. Okay, this is the material properties that related to enforcement of polypropylene using either fillers, impact modifier, or fibers. As you can see, various improvement in either fracture toughness and yarn modulus can be shown in this figure. So the use of fillers generally improves the young modulus over here, okay, but reducing fracture toughness, okay, slightly reducing with the original homopolymer polypropylene. But if you use impact modifier, you can increase the fracture toughness of the polypropylene, and then the polypropylene becomes slightly ductile. However, when you use fiber, you can see the increase of both young modulus and also the fracture toughness due to characteristic of the composite material. As for carbon steel, as you have learned in the engineering materials, you can manipulate the yield strength by heat treatment to change its microstructure from ferrite to lamella to martensite phase. So if you do rapid quenching, then you can get martensite phase, which is having a low fracture toughness but high yield strength. If you use tempering from the martensite phase, then you can get uh, a yield strength and fracture toughness is quite good enough. Here is the effect of alloying in copper. Copper is generally soft and ductile, but you can increase its yield strength by solution hardening and alloying other elements into the copper. So over here is solution hardening. Then you can get brass, which is relatively soft, but much more better, much more harder compared to pure and soft copper. Over here you have the work hardening, and here you have precipitation hardening, and then here is the combination of copper and beryllium alloys. For the aluminium, if you already know that aluminium is very ductile, okay, and also having a good thermal conductivity as well as have very low yield strength compared to copper. Okay, over here you can see the effect of hardening of the aluminum alloys, and then the effect of hardening towards to the thermal conductivity. When you put some element or alloying element or do the hardening process, then you can have an alloy, aluminum alloy. So the yield strength is significantly increased from approximately 10 or 15 megapascal towards to the highest one, which is above 300 megapascal. But the thermal conductivity is slightly reduced compared to the pure aluminum, which is around 250. Over here is should be like 150, above 100, but relatively is quite a good conductor compared to other material. Here is the effect of strengthening copper and its alloy versus the electrical resistivity. You can see that the pure copper have a very good conductivity but having a low yield strength over here. And then when you increase uh, the strength of the copper through the work or hardening, then you can get almost similar. Over here is the electrical resistivity, which is the conductivity is quite good, and then having a good yield strength. But when you change into copper beryllium, then you can have a very high strength over here, but you have a slightly increase of the resistivity. So and then when you mix with nickel or mix with zinc to become bronze or brasses, over here when you mix with copper, so over here you can have an increase of the electrical resistivity over here, but still quite low because this one is in micro ohm per micro ohm centimeter, not much increase compared to aluminium. If data for processes are to be stored in database, an organizational structure is needed. This classification of process allows information about them to be organized in a useful way, one that parallels that for materials unit 1, the three families, which is the shaping, joining, surfacing. Each contains a number of classes, okay, number of classes. That for shaping is expanded here, and that each class has many members, as expansion of moulding in this frame suggests, and each member is characterized by a set of attributes, some numeric and able to be structured, some based on text and images that are stored as a unstructured information, and one of these that of describing the shapes that a process can make requires some explanation. Okay. Shape is the most difficult attribute to describe and quantify. Many texts on processing attempt a classification. None is wholly satisfactory. So we have explored many alternatives and have finally returned to the simple breakdown shown in this frame. Here is the primary distinction between prismatic shape over here, made by process such as extrusion, rolling, and wire drawing. Shape made from a sheet by stamping, deep drawing, and uh, deep drawing, spinning, or folding over here. And then you have three-dimensional shape that involve change of section made by casting, molding, and a host of more elaborate procedures. Okay, so you have a 3D over here, shape over here, and then you have a prismatic shape over here. We now return to the attribute. This is an example of structured data for shaping process. The physical attributes include the shape and size of part that can be made, the mass range, the surface roughness, the minimum thickness section, often limited by the ability of material to flow into a narrow channels, and the precision of or tolerance of which it is capable. Structure information includes the identification of the process as discrete like stamping or continuous like wire drawing, and information about economics, most usefully the economic batch size, the production run needed to justify the cost of the dies, molds, and other tooling. The, okay, the key constraints in choosing a process are the shape, the batch size, and the material that is to be shaped, captured by the links of material. Much information about processes is specialized and best recorded as text and images. Okay, over here, such as over here, example of uses and a commentary guiding its economic use, identifying any environmental concern that is raised, and it is stored as unstructured data as shown here. So over here is the process for the injection molding. Okay, so injection molding is over here. So the process description over here for the application and so on, design guidelines, and then the economics. For example, tooling costs are high, injection molding economy for a large batch size, for example, from 5,000 to 1 million. And then you have a typical use and then the environment and so on. So you can get this one using CES EduPack Level 2 database, or you can use the granted EduPack. All three levels of the software uses the same familiar interface. This frame shows the principal toolbar and of the two of its button. The browse button let you explore the contents of a data table by roaming through to its tree. When you click the button, one on when you click the one on the button, the first level of the three families appear. Each family can be expanded and show classes and members. Double-clicking on a member opens its record. The search button allows a full text search on part or all of the records in the database, finding all the records that contain a word or word string entered by the user in the find box over here. This is the example. So far, we have discussed only shaping processes. The other two families, joining and surface treatment, can be structured and selected in similar way. This frame shows the joining tree with the class of welding expanded to show members and some of their attributes. Okay, this is the attributes. Certain attributes are unique to joining. One of these is the geometry of the joint. that the process can make. It is illustrated in the lower part of the frame. Here is the joint geometry. This frame shows data for joining process. The attributes are those that engineers use to select joining process. They differ in many ways and not unexpectedly from those for shaping. Some attributes, material size, and general economic information are common to all processes, but the rest, geometrical of the joint and the ability to join similar materials or allow the assembly and etc. are specific to joining. The key constraint when selecting a joining process are the materials to be joined and the joint geometry. So far, we have discussed shaping and joining processes. The remaining family, the surface treatment, can be structured and selected in similar way. This frame shows the surface treatment tree with the class of coating expanded to show members and some of their attributes. An attribute unique to surface treatment is the function of the treatment. Typical functions are listed in the lower part of the frame. This frame shows structured and unstructured data for a surface treatment process. The most critical attributes are the function that the treatment is required to provide and the materials to which it will be applied, assessed via the links. The key constraints when selecting surface treatment when selecting a surface treatment processes are the materials to be treated and the function of the treatment. Processes can be classified and information about them stored and manipulated in ways that parallel those for materials. In this unit, we have explored how the information for process can be organized in a hierarchical structure, okay, and then how to find the information about shaping, joining, and surface treatment, and how processes are selected to meet a set of constraints by using simple screening stages. And then the final choice of processes is guided by the insight derived from the search for document and by a more detailed analysis of cost. This is some exercise in browsing the process universe data table. You can use if you have your the software in your laptop or you have the access to the software. You can use this exercise. So 7.1, find by browsing the level 2 record for the shaping process, resin transfer molding in shaping, composite forming. So what products typically is able to be made? So 7.2, find the level 2 record for shaping process, which is the abrasive jet machining and cutting in shaping. So machining, non-conventional machining, can it be used to cut glass? So 7.3, which is the uh, level 2 record in the joining process, frictional welding in joining. Mechanical welding, how does the process work? And then 7.4, in level 2 record for the surface coating process, metal flame spraying in surface treatment. So what are the principles it use? So you can use this one to browse or you can just Google it anyway. So another exercise so that you can use, for example, over here, uh, find the record for the rapid prototype with the trade name SLS. And over here is the flexible adhesive. So which polymer are used for flexible adhesive? And then 7.7 is the vitreous enameling. What functions can it perform? So this is the summary. Okay. So that's all. Thank you very much.